Hi, my name's Steve Craig. I'm the International Sales Manager with Fluid Components International. We are a manufacturer of thermal mass flow meters, thermal dispersion flow and level switches, and we're located in San Marcos, California. Thanks for joining us today. My background is I'm graduated from Iowa State University with a Bachelor of Science, and I've been with Fluid Components for the last 25 years in engineering and sales. So let's go ahead and get this started. Today, I'm going to discuss thermal mass flow meter accuracy and installation best practices. One note is that most all thermal mass flow meters are strictly for air and gas applications. And these types of air and gas applications present certain issues that need to be addressed and understood with regards to accuracy. So we'll go ahead and get started here. To get grounded, the agenda is accuracy of thermal mass flow meters. We'll get grounded on what is accuracy, what is repeatability, and what is turndown, how they're all related together. Then we'll talk about some issues that can also be attributed to gas flow profiles and disturbances, and best practices on how to handle those. And then solutions, what's available to help with any kind of accuracy issues that are in the field. So accuracy of thermal mass flow meters. Let's get grounded on accuracy. Accuracy is the degree of conformity of an indicated value to an acceptable reference standard or to an ideal value. Basically, it's that infinite bullseye in that target. There's basically three levels of accuracy. The ideal or perfect accuracy is hitting that bullseye. That's the infinite accuracy. And that comes from a controlled laboratory such as NIST, National Institutes of Standards and Technology. And then there's a second level of accuracy, and that's where a flow meter is actually calibrated. So it's accuracy in a controlled laboratory condition. And then, of course, we've got level 3, which is installed accuracy in a process. And that is definitely not typically an ideal or controlled laboratory condition. So there's a difference. Let's talk about that. The ideal accuracy can be imagined as the infinite center of a target bullseye. It's the ideal goal. That's what we're trying to achieve. Level 2 accuracy, and this is attained under laboratory conditions. We're approaching the ideal accuracy. We're using an ideal accuracy flow meter, and it requires the finest engineering tools. Most all professional US-based calibration laboratories refer to NIST for accuracy verification. And most US-based calibration laboratories have a metrology program, which I'll talk about a little bit later. And then level 3, the realistic expectation under installed conditions. When we're talking about air and gas applications, it can be aeration basins, digest gas, flare gas, flue gas. Typically, we're talking larger line sizes. And so we're using more of a point measurement on the inside of this pipe. And typically when you're in large line sizes, you don't have the luxury of lots of straight run to be able to produce a good turbulent flow profile. And when we're talking about reference standards, typically in a laboratory or calibration facility, we're talking about using a master flow meter. This can be a DP meter, it can be a turbine meter. Typically, that's what's used in the calibration laboratory. Now, when we get installed, when we're in the customer site, typically customers will use like a stoichiometric calculation. What goes in must equal what comes out, mass or energy balance, blower or compressor discharge curves, or control valve position, and even operator experience. I've been in plants where the operator will put his hand on a pipe and he can tell pretty much just by the vibration what that flow rate is at that time. So what is repeatability? Repeatability is a part of accuracy. The random error observed in a set of repeated measurements, the combination of stability and precision, not necessarily attributed to accuracy. If you look at repeatability versus accuracy, on the left-hand side of the screen, you see dots that are relatively close together for the most part, and we would call that repeatable, but it's not accurate because none of the dots are in the bullseye, in the center of that bullseye. Accurate but not repeatable is the center, whereby we see a scattering around the bullseye and in the bullseye. So it's accurate but not repeatable, meaning that the dots aren't lining up next to each other. And then if you look at the right-hand side, we have repeatable and accurate. So with thermal mass flow meters and air and gas, they're excellent process control meters. Repeatability is better than 1% of reading, meaning those dots are all going to be aligning repeatedly in the same area. Excellent repeatability is a prerequisite for excellent accuracy. If you don't have repeatability, you don't have accuracy. Poor repeatability, poor accuracy. So if we look at accuracy as a percent of reading, what does that mean? If I say we have 1% of reading, 0.5% of full scale, there's two different accuracy statements made with that. Reading is the range of allowable percentage of the reading at any flow rate. Example, a meter calibrated for 20 to 200 normal cubic meters per hour with a plus or minus 1% of reading accuracy. So how is that calculated? How do I understand that statement? If we look at the full scale 200 cubic meters per hour indicated flow, actual flow accuracy can be 198 to 202 normal cubic meters per hour. It's 1% of 200, which is 2. So it's plus or minus 2 cubic meters per hour. If we go down to the minimum flow, the 20 normal cubic meters indicated flow, actual flow can be 19.8 to 20.2 cubic meters per hour. It's 1% of 20, which is equal to 0.2 cubic meters per hour. So we would have an error accuracy located here on the chart, whereby on the left-hand side is the percent of error based on reading, plus or minus 1% of reading, and the flow rate, where we're going from 20 all the way up to a maximum of 100 normal cubic meters per hour. And you can see the repeatability is just 1%, and all the dots are lining up 1% within those. But now when we also take the second half of that statement, I said that it's 1% of reading, 0.5% of full scale. What is the full scale? How do we calculate that? Again, example, the meter calibrated 20 to 200 normal cubic meters per hour with a plus or minus 0.5% of full scale accuracy. It's equal to plus or minus 1 cubic meters per hour at any reading. That's the important part. That plus or minus 1 cubic meter per hour at any reading is at the maximum flow and the minimum flow. Therefore, at maximum flow of 200 cubic meters per hour, the actual flow can be 199 to 201 cubic meters per hour. It's 0.5% of 200 is 1. Now at the lower flow rate, 20 cubic meters per hour, the actual flow can be 19 to 21 cubic meters per hour. 0.5% of 200 is 1. Remember, this is called full scale. So that 0.5 at full scale is applied all the way down to the minimum flow. And therefore, we have a broader error band at the lower flow rate. If you look at that flow from 20 up to 100, you can see at 100, we're maintaining that 1% of reading and that 0.5% of full scale within about the same band of error. But as we decrease in flow, that full scale error increases the inaccuracy or error rate allowed for that flow meter. So if you compare that plus or minus 1% of reading with a plus or minus 1% of full scale. So if I have a maximum flow rate of 100, my plus or minus reading, 1% of reading is 99 to 101. Plus or minus 1% of full scale, 99 to 101. They're the same. If I look at the low flow of 10 normal cubic meters per hour, 9.9 to 10.1 would be the plus or minus 1% of reading. But plus or minus 1% of full scale, again, I'm using that maximum at 100 of 1. Therefore, my allowed air flow is 9 to 11 normal cubic meters per hour. And if I look at 1, we're looking at 0.99 to 1.01 with the plus or minus 1% of reading. But with the plus or minus 1% of full scale, it can be anywhere from 0 to 2. So that full scale error has really affected that low flow allowable error. Now, you'll notice on that slide that we had a flow rate between 100 to 1. That means we have a turn down of 100 to 1. The turn down is the ratio between the maximum and minimum flow rate. So a calibrated range of 10 to 100 normal cubic meters per hour has a 10 to 1 turn down. Thermal mass flow meter technology has at least a 100 to 1 turn down. That's a very large flow turn down, and that's one of the benefits to using a thermal mass flow meter. Some manufacturers actually can go up to 1,000 to 1 turn down. To give you an idea, compared to other types of technologies, an orifice plate typically has a turn down of 4 to 1. So they would read between 40 to 10. Or a turbine meter is 10 to 1. A vortex is typically 12 to 1, and ultrasonic goes up to 400 to 1. So how does this affect the turn down, affect the accuracy allowable error band? So accuracy at low flow is better with a low turn down. So that's one of the things that you have to keep in mind when selecting what flow range you want that meter calibrated to and what's really required, because that does begin to affect the accuracy at the minimum flow. So for an example, flow meter accuracy is plus or minus 1% of reading plus 0.5% of full scale. So if we calibrated the meter with a 10 to 1 turn down, minimum flow accuracy is plus or minus 0.6 normal cubic meters per hour, which is equal to 9.4 to 10.6 normal cubic meters per hour, or 6% in accuracy. If we calibrated to 10 to 1,000 normal cubic meters per hour, whereby we have that 100 to 1 turn down, the minimum flow accuracy is plus or minus 5.1 normal cubic meters. That's a very large error range allowable, which is actually equivalent at that 10 normal cubic meters per hour of 51% inaccuracy band. So turn down is critical when you're looking for accuracy in a flow meter. To give you an idea though, some manufacturers actually have a statement of the maximum full scale error is 5%, period. So therefore we still use the full scale error up to 5%, and then it stays the same at 5%, even to the minimum flow. Calibration test labs. Calibration should be performed utilizing only NIST, National Institute for Standards and Test Technology, traceable equipment and instrumentation. They should also maintain a metrology program, meaning that they have annual service and verification on their primary meters that are used to calibrate their meters, meaning that if FCI is using a turbine meter to calibrate thermal mass flow meters, every year we send that back to a NIST approved agency and have them verify and recalibrate that turbine meter, that master meter. It's very critical that a metrology program is maintained. And when you get the calibration data sheet, the calibration certificate, it should have all of the information regarding when was the last time that master meter, that primary meter, was calibrated. And it should be within an annual type recalibration or verification. And accuracy metrology, how it all actually comes about. So you have NIST, which is at the top of the screen, National Institute of Standards and Technology. They maintain bell provers and sonic nozzles in their lab. And that's the second row. The third row is those bell provers and sonic nozzles, they calibrate their own sonic nozzle or turbine. And those are used as the transfer standard to the manufacturer's meter, primary meter, calibration meter. And that's where you get into the sonic nozzle or turbine or rotometer that is sent back to that NIST calibrated facility. And that's where we verify the meters that we're using to calibrate our meters. And then the last row is the measurement instrument. That's the meter that's been calibrated based on the primary meter that the factory is using. So in summary, installed accuracy can be verified by the customer's reference standard, and end user satisfaction often depends upon coming to agreement over the standard being applied and the recognition of how real-world conditions differ from the ideal conditions in the flow lab. And so that's where we're going to go with this next portion of our meeting today, is what is the real world conditions and how can they affect compared to the ideal conditions in a flow lab. So some of the questions to assure satisfaction with instrument accuracy. What is the accuracy or repeatability requirement? What is the real requirement? Is this just process control, which is typically you're looking more for repeatability? What is the pipe or duct size? That's going to affect any kind of accuracy issues. Where is the probe going to be located? How much upstream and downstream straight run is available? Do we have elbows? Do we have gate valves? What is the disturbance upstream and downstream? And how far are they located from where the meter should be installed? And then, is the reference meter or blower measurement in actual or normal? Many times the flow meter that's installed is compared to a blower output. And that blower output typically is in actual cubic meters per hour, or standard cubic feet per minute, as compared to a thermal mass flow meter where it's a standard, it's a normal, it's based on pressure and temperature. And therefore, you cannot take a blower curve and use that to compare to the flow meter without making corrections for pressure and temperature. And as you know, gas is compressible. It is affected by temperature and pressure. So it's very important that we're not comparing mass to an actual blower curve. And then, is a flow conditioner required because of lack of pipe straight run? I mean, if you have less than 10 pipe diameters or 15 pipe diameters, you're going to want to look at a flow conditioner probably in order to condition the flow profile. And we'll get into that a little bit later. And are multi-point sensors required? Sometimes you can use multi-point sensors. You can use many flow elements going back to one transmitter and they're averaged for flow output. And then calibration considerations. Is it air equivalency to the actual gas and extrapolations due to limitations of the calibration test stand? Many manufacturers only do air calibrations and they'll do a equivalency based on that. And then extrapolations. Some calibration test labs have limitations on what the minimum flow is and what the maximum flow. So if your application is above what the test stand can do, then they just take that nonlinear curve and they extrapolate it out. That's not always the best situation. So you want to make sure that your calibration is performed on a test stand with the actual gas and that extrapolations aren't performed on it. And then, is in-situ calibration required if in a large pipe diameter? Let's say 24 inches or larger. You can still use a single point and do an in-situ field calibration, meaning that you have the flow meter installed, you pull it out, and you put in like a S-style Pitot tube. and you perform a cross-sectional representation or measurement across that pipe to find out what that average flow is. You insert the flow meter back in, compare it to what the pitot tube DP measurements are, and you can make a correction to your insertion flow meter to match the same as the pitot tube traverse. And then what reference standard is used to verify the accuracy? So let's talk about some of the issues that can arise if you don't have straight run available. To get grounded, recommended flow meter installation, types of gas flow distortions, typical gas flow disturbances, and then what solutions are available. Typically with an insertion point measurement flow meter, that can be any kind. It can be a turbine meter, it can be a thermal mass flow meter, it can be an orifice. What's required is a certain amount of straight run. And typically we install the flow element, the sensing element, at the center line of the pipe, as depicted in the top two. One's a flanged and one's a threaded process connection. And then how much straight run? Standard in the industry says 10 pipe diameters of straight run upstream and 5 pipe diameters of straight run downstream are required. But what this does is it provides a certain confidence level, a 95% confidence level, meaning that there are, of all the disturbances out there, if you have that much straight run, it's going to eliminate any kind of flow profile disturbances. But there are other disturbances that require a longer straight run than 10 and 5. Some go all the way up to, if you have like a gate valve or 2 elbows out of plane, it can be 20 pipe diameters of straight run requirement upstream and 10 pipe diameters of straight run downstream. So what we're looking at is typically in a 18-inch or smaller diameter pipe, you have a standard turbulent flow profile, and whereby friction of the wall is actually dragging the velocity of the flow down. Therefore, velocity, the maximum velocity, is actually at the center line of the pipe. When you get into 18-inch and larger pipe or duct diameters, then that friction plays less of a role on that flow profile, and it's more of a flat flow profile. And therefore, it needs to be calibrated differently. So also make sure that if that calibration test laboratory is calibrating your flow meter, you want to calibrate it to either the standard turbulent flow profile in the top, if it's 18-inch or smaller. If it's 18-inch or greater, you want to calibrate it to a flat flow profile, like a wind tunnel type calibration. And some of the types of gas flow distortions that we see typically, number one is flow profile distortion, like a T or an elbow upstream, whereby the velocity isn't, the maximum velocity isn't necessarily at the center line of the pipe. That's going to create some inaccuracies in the flow measurement. Or swirl, if you have 2 elbows out of plane. Typically, this can be troublesome because the flow profile does distort quite a bit. And then something that is not discussed much is Reynolds number transition. If you have a smaller diameter pipe with a low flow, there's something called Reynolds number transition, and it's affected in the low flow portion of the flow. So Reynolds number transition, I think everyone understands the flow profiles that we talked about, but let's spend a moment on Reynolds number transition. If you look at the low flow, and the low flow has a Reynolds number 2000 or less, that maximum velocity at the center line of the pipe is very great. We call that a laminar flow. And then as you go between Reynolds number 2000 to 4000, it transitions into a turbulent flow profile, which on the upper right of that chart, you see more of a flatter shape. And it's during this transition in these low flows that we have to be careful. So make sure that the sizing software that the manufacturer is using provides what the Reynolds numbers are, because if that transition period happens, it does tremendously affect the accuracy of the instrument itself. To give you an idea, the blue line, which is the bottom line where it starts at we begin to flow, no flow, and that line begins to drop. And then all of a sudden we hit the Reynolds number transition between 2000 and 4000, and all of a sudden it starts climbing again. And what that's showing is lower flow. So it does affect the accuracy. It can even reverse the actual what is flowing. So when we get into this Reynolds number transition, we highly recommend that some kind of flow conditioner is used to eliminate that transition. And then some of the ideas about recommended flow meter installation. One of the things is if you are in a gas and you don't want that gas to have to shut down to take the flow meter out, highly recommended that you use a ball valve with a packing gland assembly that's located on the flow element itself. So here we've got a depiction of a flow meter that's inserted on the left-hand side, normal operation through a ball valve, and there's a packing gland located on that flow element that's flanged to the ball valve itself. What we do is, if we want to remove that flow element without shutting down the process, we loosen the top nut on that packing gland. That allows us to extract, step 2, the flow element and the probe up into the packing gland itself where it clicks in. And then step 3, we close the isolation ball valve. And then step 4, remove the probe from the process connection. And you never had to shut down the process. One of the things to keep in mind also is there's 2 types of thermal dispersion technology. One is constant temperature, and the other one is constant power. The constant temperature tends to have some issues with the biogas, the digester gas, because biogas is pretty wet and it does have a lot of debris that's in it. So it's highly recommended that a constant power type thermal dispersion technology be used, because the constant power, what it does is it elevates the temperature of that active sensing element. It elevates it above the temperature of the dew point of the gas, which means that moisture cannot collect on it, and therefore moisture is what collects the debris. So as long as you don't have moisture on that active sensing element, then you have a good accurate flow reading. And then another good flow meter installation best practice would be to locate, if you have water vapor in the line or you have moisture in the line, locate the flow meter 45 degrees from the side. Typically when you look at a flow meter, it's top mounted. But if you have water vapor or condensate in the line, that is not the best scenario, because that water vapor is going to condensate on that probe. It's going to run down, the water droplets will run down the probe onto the active sensing element, and that will cause problems with accuracy. So if you have gas, if it's biogas and you have water vapor, that water vapor is going to collect on the probe and run down onto the active sensing element. Not a good best practice. If you come in from the side, the water vapor may collect on the probe, but it will drip down away from the active sensing element. And then if it's really wet, come in 45 degrees from the bottom. And here I've got a picture on the right-hand side whereby this is a blower. It's bringing in outside air, and they're actually collecting 20 liters of water out of this. You see the drain line in the pipe, which is the black pipe, and that's how they're making the measurements, how much water they're collecting. But the flow meter is operating just fine. Any kind of condensate that's building up on the probe is running away from the active sensing element. And there's another option or solution that's available, and you can use a moisture shield. And here we have shown on the left-hand side, top picture, where the gas is passing into this shield, the shroud, and that shroud has a mesh screen. That mesh screen actually knocks out any kind of water droplets. And this shroud also has drain holes so that that water can drain out of that shroud. And if you look at the bottom, that's the outlet side. That's the back side of the top picture. And there's your active sensing element or your flow element. And that's staying clean because the water droplets are getting knocked out using that. This is just an option that's available. It's great if there's a lot of water vapor entrained in the gas. And then some issues that you find in the field that if you identify before you purchase the flow meter, you can stay out of these types of situations, such as the enclosure conduit port facing a wall. Here, they ordered the flow meter with a left to right flow, and so they installed it left to right, and as you can see, the conduit ports are actually facing the wall, so they need to reverse that. Or flow sensor not parallel to the flow direction. Here we've got 2 meters in line to each other, and you can see where you can visibly see where the conduit ports are going any direction. There's really no systematic way of showing the flow, which direction the flow is going. But on most all flow probes, flow elements, they have a flat with an arrow showing keep this perpendicular to the flow, meaning there is a certain way to install a flow element in the application itself. And it does become critical if it's not within 10 to 20% of, or 10 to 20 degrees of how it should be installed. And then erosion, damage due to, let's say, cement material. Here you see a probe on the left-hand side, and you can see there's a lot of corrosion or erosion on that probe itself. There is an alternative available. Some manufacturers use a chromium carbide coating, and that provides protection against any kind of erosion that can occur on the probe itself. It's an alternative. And then corrosion damage. This one's showing H2S, hydrogen sulfide. Recommended Hastelloy C wetted material. So it becomes critical also that you understand the process gas and what's compatible, what flow element material is compatible with it. And then a lot of flow meters also have, for process connections, compression fittings. Typically in lower temperature processes, you can use a Teflon ferrule, whereby you can crimp that into place, tighten it, and you can do it repeatedly. But if you use a metal ferrule, it can cause damage to the probe itself, so it's recommended that you crimp it once and that you don't repeatedly keep removing it and crimping it, removing it and crimping it. And then the other one is, and I showed you this picture before because it was a great picture of an application with a blower and the water vapor, and they were collecting 20 liters of water an hour. But here it also shows an inadequate installation whereby the electrical conduit port, the cable gland, is facing up. This is something that you don't want to do because any kind of water will leak through that cable gland. You can have the best cable gland out there and you still can get water damage to the flow probe electronics. And then if you have diameters that are greater than 18 inch, I mentioned that you can have multiple sensing points and then going to a flow transmitter and averaging that for one flow output. Typically an 18-inch diameter and larger, this is what's recommended. And what we do when we locate these flow probes, we locate them in an equal area, meaning that area number 1, that total area volume, is the same as area number 2. You want that flow, those flow probes located in equal areas in between those two areas. And that same, of course, goes if you have 4 points, that's the location. You can also have multi-points on one flow element, meaning that you can have, here we're depicting two on the left-hand side, two probes with 2 points each in the blue. Those are the points. And we're using 4 of them and averaging the flow on the inside of this 2,000 millimeter or 78-inch duct. And again, all we're doing is we're locating those sensor points in the equal area. So if we're using 2 points, we divide the area in half and locate the sensor points in the center of each half, and so forth. If you're using 3 points, it's 33%. Locate the sensor points in each area in the middle. And this is all based on the 10 CFR 50 and ISO 1007-80, how to divide cross-section into equal areas. And I also talked about Pitot tube in-situ field calibration. This is a great alternative in very large ducts or pipes, whereby you have the base accuracy of the instrument, which you receive from the factory, and you determine the number of sensing points that are required by using the factory's sizing software program. And typically you don't have the 20 upstream and 10 downstream straight run. So therefore, your installed out of the box accuracy will not be the same in this large duct or pipe. So we recommend using an in-situ calibration using Pitot tube traverse method per 10 CFR 50 guidelines, whereby on the right-hand side, you see the picture and you see the flow element there that's installed in the silver metal box. And you see there's actually a few of those probes in this large duct. Flow is going from bottom to top. And we located the Pitot tube ports just above or about 12 inches upstream from the flow meter, the flow probe itself. So we put multiple Pitot tube ports in. We take that S-type Pitot tube, traverse data points, the flow profile all the way across that. We take that and we run the numbers, we come up with an average flow, and we can actually correct the flow meter in its installed accuracy. Not only that, but you're using another third-party meter to confirm the accuracy of the flow meter itself. And then gas flow conditioning is another option. Typically in smaller pipe diameters, 18-inch and smaller, you can use anything from a perforated plate to a tab type to a tube bundle to a vane. We offer a insertion panel type flow conditioner whereby we're just creating a flat turbulent flow profile. And what that does, it allows us to remove any kind of upstream disturbance to the flow meter. After the gas passes through this VIP, this insertion panel flow conditioner, it becomes flat and turbulent. And therefore, if the flow meter is calibrated at the factory to this flat turbulent flow profile, and then you take that same setup and you put it in the application itself, it's going to always have the same flow profile. It's going to be accurate. And typically we locate the flow conditioner 3 pipe diameters upstream from the flow meter itself. And here, this is kind of a busy chart, but it does give you an idea of what effect different disturbances have. Here we have a flow meter with no flow conditioning, and it up 6 diameters upstream, we have different types of obstruction. The blue line that's in the center line, so on the left-hand side of the chart, you have your error percentage, and then you have increasing flow from the left to the right on the bottom. And you can see the flow meter reading with no flow profile disturbances is the blue line, and it's right there around 0%. But let's look at the yellow a gate valve 30% closed, and now our error is way out of our range based on that. And even if you have an elbow upstream, that's the red line, you can see we're as much as 12% off on the low end, going all the way up to around 4% off on the low end. So every disturbance has its effect on the accuracy, and that's why we say that we have a 95% confidence level that for 10 pipe diameters upstream and 5 pipe diameters downstream, we're going to be accurate. But now if we install some kind of flow conditioning device, 3 pipe diameters upstream from the flow meter, all those same disturbances on the previous slide are now brought within the accuracy statement of the flow meter, meaning that we've conditioned that flow to where it's a repeatable, highly accurate flow measurement, even with 6 pipe diameters upstream of a flow disturbance. I'd like to thank you today for joining this training session, and feel free to contact me if you have any questions. Thank you.